the signal as a function of waiting time. Okay, so we can probably pump here, which is pumping into eigenstate near canonical section, or we can pump into here, and this is eigenstate far from canonical section. And by look at the specific input frequency, excitation frequency, and plot the signal as a function of a delay time, we can see this kind of map, dynamical map. And this dynamical map tells us that the vibrational wave packet dynamics for canonical section system and avoided crossing system are very, very different. In avoided crossing system, you see kind of a simple vibration. But here is totally different. So very drastically different results can be revealed by this kind of dynamical map. And we can actually do further Fourier transform along this waiting time to get Fourier transform the result frequency map, frequency correlation map. And this map on canonical section signal and avoided crossing signal show very interesting differences, because in avoided crossing there's no peak here and it's sitting right on its frequency. But in canonical section dynamics, the peak actually shifted and there's a cross peak here. And we should focus on this cross peak. When we focus on this cross peak and look at where this cross peak come from, we can identify that it's actually coming from an interesting dynamics described by this two-sided double-sided Feynman diagram. You don't need to know the details. The key is here. Basically, to have this signal, you need to have a transition like a coherence of E3, E4 to coherence E4, E3. So it's a complex conjugate inversion of the coherence signal. This kind of a coherence transfer, should be a signature of a Berry phase. This inverse pi phase effect can actually be observed using two-dimensional electronic vibrational signal analysis. So this is the way we propose that people should do experiment and use this to specifically look into the Berry phase effect in canonical section systems. Okay. So this is the kind of summary of our result in this simulation here. Okay. So I think in conclusion, we developed theories that allows us to calculate accurate quantum dynamics in condensed-phase molecular systems with low cost. And with this theory, we can simulate experiments that could be, that predicts some experimental result that could be actually used or carried out in a real experimental group. So that's what we do in this regard. Okay, so I should acknowledge my students, Huang Tao, who actually work on this quantum Schrödinger-Langevin equation approach and this 2D UV data. And Huang Pinze work on this pure-dephasing approach, and Liu Junhao work on this 2D IR signals and the founding agencies. And I thank you for your attention.
Thank you, Professor Johnson, and a very nice talk. So any questions from audience? Please.
Hello, thank you. So I have questions about the quantum Langevin equation approach that you're using. So I was wondering, because you're modeling the dissipation as a friction in the quantum Langevin equation, right?
Yeah.
So have you considered using the master equation approach for the system, or maybe it's just not applicable?
No, actually we can use master equation approach. But the thing is, in order to treat vibrational dynamics correctly, we need to include many, many vibrational states. And the size, the growth of a vibrational space actually is exponential. Okay, so you include 2 modes, 3 modes, 4 modes. It grows exponentially. It's very difficult to treat. So if you use a quantum master equation approach and you treat the problem in using density matrix, it's a huge n to the 4th order. But in treating using wave function, it's more manageable. That's why we developed this wave function-based approach.
Okay, thank you.
So any other questions?
I would like to ask a very naive question. So when we think numerically, usually it's not exact. But so what do you mean when you say numerical exact?
Numerical exact, yes. Yes.
Can you
so,
clarify that?
So those methods actually use a basis to expand the dynamics. And that allows you to, if you include enough basis functions, you can describe the dynamics exactly, basically. But the calculation actually grows, the cost of a calculation grows very rapidly. So it can only be applied to smaller systems. And for some, in some group, actually, even in Professor Norris' group, they develop code that are very efficient, that actually can simulate system with enough size for 10 or maybe even to 100 sites. That's possible nowadays using HEOM. But still, we want to apply, or we want to see, look for perturbative methods that actually allows us to gain more physical insights into the dynamics. Yeah.
Right, thanks.
Okay, so any questions? Okay, so please.
Sorry, as an experimentalist, I may ask a very naive question, but what I understand is that vibration mode is can be modeled as an phonon vibrations.
Yes.
And we are working on superconducting qubits, which consider as an artificial atom.
Yeah.
And then, so can we discuss in terms of phonon interact with this artificial atom using your model?
No problem, actually. In this case, actually, we use a simple friction operator. It's time independent. So we call this actually a white noise and Markovian friction. Okay. And actually, we can replace this with a time-dependent friction kernel. And that time-dependent friction kernel can be used to model arbitrary path. Actually, I mentioned that we have a research of try to characterize quantum noise in IBM-Q systems. And there, we very specifically look at the statistics of a noise. And we can build up the distribution function for the noise, basically a spatial density function that exhibit on those IBM-Q quantum processor. And we actually can use those spatial density to plug into our theory to do calculation to model how the quantum artificial atom behave under a realistic noise measured in our experiments. Yeah. So it's possible.
Right, so let's thank Professor Zheng again.
Thank you.
And we are